Hello everyone, I am Dr. Subhasish Saha, Assistant Professor in Physics, Department of HNS, MLR Institute of Technology, Hyderabad. So today we will discuss about Bragg's law of diffraction associated with some lot of methods we will discuss today to determine the crystal structure or crystallographic structure from the Bragg's law of diffraction. So over today's topics is little bit, I will go to the deeper details about these topics. Before going to that, we can just give some overview of this today's lectures. So today we will discuss about X-ray diffraction, that is Bragg's law explained by the Braggs. Next topic is powder methods. It is one of the X-ray diffraction method. Next is X-ray diffraction series formula. From there we will discuss how to determine the crystal structure for nanomaterials. Third is another topic, scanning electron microscopes, where also we use the concept of Bragg's law. Okay, so this is the overall overview of today's lecture. Before going to that, what is X-ray diffraction? What is Bragg's law? We already discussed about that a crystal structures is basically contain lot of space points. Okay, lot of space points is there, and those space points occupied by the atoms, ions, or any group of atoms. And so crystal is contain several parallel equispace planes, okay, lattice planes. So this is suppose on a crystal structure there are two parallel planes. Okay, we know about this crystallographic that there are planes are basically depends on the lattice parameters. Those are A, B, C. There are three parameters, as well as there is a interfacial angles is also there. From there we can give the idea about the MLR indices, and that from there we can give some the orientations of the crystal plane from the MLR indices. So crystal is contain there are lot of equispace parallel planes. So there are two planes, suppose this one of the plane and this another plane, those are two parallel planes. Now what is happening, suppose a parallel beam of X-ray, it comes and incident on a crystalline solid, okay, and it is reflected from the parallel planes, and when it comes to this X-ray beams and falls on the crystal surface or two lattice plane, and those are reflected, okay, and after reflections those rays are interfere. When those are interfere, when the constructive interference will happens, then we can get some diffraction pattern, and this is only occurs when the light is incident at a certain angle. Okay, that angle is called glancing angle. Okay, if the angle of incidence and angle of reflections will be same, those will be scattered with the same angle, then the constructive interference will be happen. When the constructive interference will happen, we get the maximum peak intensity. Okay, when we get the maximum intensity or that the brightness, from there we can got some diffraction pattern. Okay, so this is the idea about the Bragg's law of diffraction. So the condition is 2d sin theta equals to n lambda. So we know that lambda is the wavelength of the incident X-ray light. Okay, d is the interplanar spacing, so the space between two planes. Theta is the glancing angles, okay, at which angles light is incident, for that constructive interference happen, that is called glancing angle between incident ray and the crystal plane. Okay, that is the angle. Wavelength is lambda, it is the wavelength of the X-ray light, and n is the order of diffraction. Okay, now the question is, why we use X-ray for to determine the crystal structure. So why not others electromagnetic waves? Okay, why only X-ray? Because the answer is X-ray can be diffracted by the crystals because the wavelength of X-ray, the lambda and the interplanar spacing in the crystals are in same order, which is 1 angstrom order. Means lambda is the order of interplanar spacing, which is angstrom order. Okay, 1 angstrom order. Okay, that's why we use X-ray. Now we have to prove, we will prove these things. Bragg's law, this condition will prove how to prove these things in the next slide. Suppose how there is a, consider a set of parallel crystal planes, okay, which is separated by a distance d. Okay, now a monochromatic X-ray beam, monochromatic means the lambda value is constant, single valued or single colored X-ray beams. Okay, monochromatic X-ray beams having wavelength lambda is incident on those planes at an glancing angles. These two beams are falls on the two plane. There are two planes is there. Now two rays are reflected from two successive planes. There are two successive planes, two rays are incident and those are reflected from two successive planes. So there is one path AB incident ray and those are reflected along the path BC. Another ray is falls in the second parallel plane, that is incident is DE and reflected along DF. Okay, now the second ray, this is ray 1 suppose and this is a ray 2. The second ray travels extra distance compared to first one. So what is the extra path traveled by the ray 2 compared to ray 1? That is this one. Okay, the extra path traveled by this thing is, that is called path difference between ray 1 and ray 2, that is GE plus EH. Okay, so from the geometry we can say if it is in theta, that one will also theta, and since this is perpendicular, if we draw a perpendicular on from this point B to on this ray 2, that is perpendicular is BG, sorry, that is BG. So if it is 90 degree, then this will also be theta. Okay, if it is theta, so what is this G? G will become D sin theta, because that is D, this one is D, this one is D and this angle is theta, so this will be D sin theta. Similarly EH also come D sin theta. So total extra path traveled by the ray 2 is 2D sin theta. 2D sin theta. Okay, so the condition for constructive interference is the path difference must be equal to the integer multiples of wavelength. So 2D, this is the path difference, is integer multiple of the wavelength. So 2D sin theta equals to n lambda. So this is the mathematical expression for Bragg's law of diffraction. Okay, and this is for constructive interference only. So constructive interference, when the constructive interference happens, then only diffraction patterns will be occur. This means where the intensity will be maximum in that case. Okay, then these conditions will follow. So this is some explanation about the Bragg's law of diffraction. Now come to the, we use this Bragg's law of diffraction to determine the crystal structures using several methods. One of the method is powder method. Okay, what is powder method? So what is powder method? Before going to that, what is the purpose of these things? Basically we determine the crystal structure, okay, of a material. Now how can you determine the crystal structures? For that, to determine the crystal structure, first condition is it must satisfy the Bragg's law of diffraction. So what is that condition? 2D sin theta equals to n lambda. So in this case, if we look into this equation, there are two things is variable. One is theta, another is lambda. In some cases, lambda will be varying, theta is constant. In some cases, theta will be varying, lambda is constant. In some, so there are two variables. When some cases lambda vary, theta constant, in some cases theta vary, lambda constant. Okay, we already know some things about to determine the crystal structure is Law's methods or rotating crystals method is there. In Law's methods and rotating, in those cases, some cases lambda will be vary, theta is constant. In rotating crystal method, theta will be vary, lambda is constant. So in this case also, we will come to that. If we know about the theta and lambda, then we can easily determine the D, and D is basically interplanar spacing. I know that the D is interplanar spacing contain the value of lattice parameters as well as Miller indices HKL. So D gives some primary idea about the lattice parameters and what is the Miller indices. So if we got some those ideas, we can easily get some idea about the crystal structure. So to determine the D is very important to know about the crystal structure. In this powder method, what do we use actually? First of all, it's not like a Law's or exactly not Law's methods or rotating crystal methods. In those cases, we take a crystal structure at format, some shape is there, but in this case the name is also given that it is powder methods. Means you first take a crystal and you make a powder of those. It is a powder form of polycrystalline materials. Okay, when you make a dust, okay, then and that is kept inside some capillary tube, okay, or some test tube we can say. You first take a crystal and you make it, first you scratch those things and it's make a very fine form of powder, okay, of that crystals. So then, and after that you kept inside the capillary tube, okay. So that what will happen now in this case, how can you determine this D value? Before going to that determining D value, we need to know about this. In this case, we need to know about the lambda value and theta value, right? In this case, in powder method, first of all, we are not rotating the crystal, okay. The powder form of the capillary tube, the powder is contained inside a capillary tube, that will not rotating, okay. So, and we use some monochromatic X-ray light where lambda is constant. If lambda is constant means definitely we should vary the theta, right? Okay, definitely we should vary the theta. The question is how we vary the theta value, because we know in Law's methods we vary the lambda value and theta is constant. In case of rotating crystal methods, we vary the theta value, lambda is constant. In these powder methods, we also use monochromatic X-ray beams. If we use monochromatic beams, means lambda is constant. Lambda is constant means definitely we should vary the theta, okay. But we are not rotating that capillary tubes, we are not rotating that crystals, okay. Then the question is how we vary the theta value, and from that we can get the diffraction patterns will forms on the photographic plate. I will come to that point. Now the question is how can we vary the theta value? Since we are not rotating these crystals, then how can we get the, how can we vary the theta value? In this case, the method is little bit different. Suppose a capillary tubes which contain the powder form of the crystals, okay. Suppose there is a powder form, it is a capillary tubes, there is a powder form of the crystals is there, okay. Okay, there are a lot of dusty tiny crystals planes are there, okay. Now what will happen, it's like a, suppose it is a powder form of the crystals. In that powder, lot of crystals planes are there, dusty very fine crystals planes are there, okay, having the different orientations. Suppose a particular set of orientation, suppose either it is 100 or 010 or any kind of particular plane, suppose 111 plane, okay. So there are lot of crystals planes are there having the different orientation. Suppose I take only particular plane 111 crystal planes. Is there is one crystal plane particle crystal plane is that is 11 plane. Another point is there, another fine crystal planes, that is also one plane, but those are different orientation is there. Okay, it is not that some plane is that in these directions, that is all are particular set of planes. Suppose a particular set of planes is all are assuming one plane, but having the different orientation. Suppose someone is one plane, someone is in this direction, someone is this direction, someone is that, someone is that. So in this way, particular set of planes, but their different orientation is there. Okay, now what will happen, the light is falls on this crystal planes, and from this crystal plane those are reflected. Okay, and now you just make a photographic plate, and the reflected lights will fall on that plate, and those will form a diffraction pattern. Okay, again I am discussing one more times how it is happening. Actually, due to the different orientations in different angles, diffraction patterns will be formed. A little bit more clarifying these things. Suppose a capillary tubes contain powder form of the crystals. Okay, and that is hanging by some wire. Suppose one of the capillary tubes contain powder form of the crystal, and that is hanging by some wire. Okay, this one capillary tubes contain powders from the crystals. Now in these capillary tubes, now what we did, we just keep some photographic plate we kept. Okay, in a around these things. Okay, it is a one photographic plate is there, and one crystal, the capillary tube is hanging which contain crystal powder. Now what we did, now incident X-ray is coming. Suppose from one direction incident X-ray beams is coming, and that is fall on the crystal powder. Okay, from there the light will be diffracted from crystal planes. Since crystal planes have different orientation is there, so due to different orientations in different positions, the diffraction patterns will be created over the photographic plate. This means how it looks like. It looks like, suppose looks like, suppose crystal capillary tubes contain powder. Okay, and light is coming, X-ray, monochromatic X-ray beams comes and okay fall on the crystals. From there it is reflected or deviated. Or now what is happened, after those reflected rays are take the image of this diffracted rays on a photographic plate. Surrounding of these crystal structures, one photographic plate is there, which is capture the image or the diffraction patterns. Okay, on the photographic plate. Okay, it's the overall idea. Now what will happen, suppose this is incident ray is coming, these are capillary tubes which contain the crystal structures, light is comes and fall on these things, and after that it is deviated or diffracted in different directions. Okay, so in these powders there are several tiny crystal planes is there. Suppose particular one plane is there, and those are different orientation is there in that powder. Okay, so due to these different orientations, light will be diffracted in different directions. Okay, some light will be different for one crystal plane, light is diffracted in these directions. Suppose okay, another orientations, another angle of plane is there. Suppose this is one plane, light is comes, it is totally go. Another plane is like that, light is falls and in this direction. Okay, and it is also in this direction. So in this way, in different directions, diffraction patterns is formed. Okay, and that is be captured on the photographic plate. Now after that what will happen, suppose due to these different orientations, different several circles is forms. Now how actually take care of these things, look into this diagram. So suppose this photographic plate is now this circular photographic plate, we just make it a straight. Okay, we make a just a straight of these things, then what it looks like, that diffraction patterns is like in these natures. Okay, this means suppose there is a photographic plate is there, there is a photographic plate. Okay, in this there is a photographic plate is there. Okay, in this photographic plate, now light is comes and falls on these things. Okay, in diffraction patterns is formed, there is one circle. Okay, so in this case suppose, how can I discuss about these things? Suppose this is a photographic plate, this is crystal, one of the crystal, a light is comes and falls and it is diffracted. Okay, in this direction, another is diffracted. Okay, so that makes some circle, right, on the photographic plate. So fraction of these things on the photographic. Now if you like another crystal orientation is there, that is in different direction, that is diffracted, so that is another circle. Okay, so in this way, if you take these things, small part of these things is showing. If you remove on this photographic plate, a small segment of this circle is occurring, like it looks like that. It's a circle, it's formed on the photographic plate. This is a small fraction aperture or segment of this circles is observed. Okay, for different angle, different orientation of the crystal plane, the different circles are formed on the photographic plate. That's why it is theta 1, theta 2, theta 3, due to the different orientations of the crystal plane. So this is your, suppose, entrance hole, light is entrance exactly, and this is your exit hole. Okay, whereas light is just fall directly and straightly it is goes out. Apart from that, the diffraction patterns is formed. So here is a main point is, we consider only those diffraction patterns, only those are make the diffraction patterns which is take care the constructive interference, right? Light is comes and those are interfere, and after that constructive interference is happened. So then only the light which is brighter one, which the intensity of that light is which is bright, that one only that will only consider to for this diffraction pattern. Okay, or diffraction in this case. Now I will come to these things. So I hope this diagram is clear. This is a state of this photographic plate where the several circles are formed. Okay, several circles are formed. It is a part of these circles. Okay, this is like that for different orientations of the crystal plane of that in the powder. Different angles is there. Now come to this little bit more clarity. Suppose there is a photographic plate and there is light is comes. Okay, this is incident X-rays comes and fall on the crystal plane at a glancing angle theta. Okay, and it is diffracted in this direction. Okay, so it makes an angle theta also. Glancing angles are equal, so its angles. Now it is vertical opposites of this plane. So it is, if it is theta, this one is also theta. So total is 2 theta, right? So this is 2 theta. Okay, and if it is also reflected in this direction also, if it is 2 theta, this is also 2 theta. Total is 4 theta. Now what is these things? This is the arc of this circle. There is one circle is there, right? In this circle there is the arc. Okay, so arc means this one. Suppose this is the arc. Suppose this is the arc, that is S. Okay, okay. So that is S. Suppose the distance, this is your S. Okay, this is the S1. Okay, and the distance from the crystal plane to photographic plate, that is R. Okay, so we can, from this geometry we can say this total 4 theta equals to S by R when in radian, when theta is very small, right? Now it is in radian, then theta is S by 4R. In degree it is 180 by pi. Now the distance from the crystal to photographic plate, that is R, that is near about 57.3 millimeter in generally, that is the radius. Basically crystal plane to photographic plate, that is the distance, that is basically radius. Okay, and where the diffraction pattern is formed, that arc is S. Basically one of the circle is there, okay, one of the circle. So in that circle, what is that curvature is formed, right? This is a small part of this circle, right? So what is the distance? That is S, okay. If that is S, that is the arc of this, the circle is formed, right? What is this periphery? That is S, okay. This one is S and this is the R. Then we can easily say 4 theta equals to S by R. In generally, the distance from the crystal to photographic plate, that is given, usually we can take at 57.3 millimeter, and theta is, then we can say theta equals to, if we substitute those values in this for equation, R value, we can easily get theta equals to S by 4, right? Theta equals to S by 4, and by scale we can easily measure the S value. If we substitute the S value, we can easily get the theta value, okay. So this means for one circle S value is 1, for another circle S value is different. So in this, for different S value, S is different, S is different, and theta is also varying. Theta is also varying, okay. So we can, in this we can vary the theta, okay. Now if lambda is monochromatic light, lambda is constant. If we now in this we can easily determine the theta value. If we know theta and lambda, we can easily determine the D value. When we get the D value, we can easily give some idea about the crystal structure. So this is some idea about the powder method. Next is X-ray diffraction methods, and we can discuss about series formula to determine the size of the crystallite in nanomaterials. So we already discussed about what is these things. Come to these diagrams. XRD is a technique used to determine the crystallographic structure of a material. So we determine the crystallographic structure, okay. Now, so this is a simple diagram. Suppose one sample is there, there is a X-ray tube, from there light is coming and falls on the surface, and those are reflected, and those reflected lights are interfere, okay. When the constructive interference happen, the diffraction patterns will form, and that is gives by the Bragg's law, 2d sin theta equals to L lambda. We know about these things, and in this case we know about, already discussed, D is the interplanar spacing. If we know about the D, we can easily say about the crystal structure. So diffraction patterns give some fingerprint of the material structures, right? We can use, we have used the detector. It is a, we can, if you detectors, we rotate the detectors in these directions where the maximum intensity will be observed. In that place, I can say, yeah, in this place diffraction patterns is formed due to the constructive interference. We rotate the detectors, okay, and from there we can get the maximum intensity of light, okay, for different glancing angle. So we can say, we can vary the intensity, okay, intensity with glancing angle. Where the intensity is maximum, okay, intensity is maximum, we can say there is constructive interference happen. Due to that constructive interference, diffraction patterns is formed. So this is, from there we can, if we got the diffraction patterns, from there we can give some idea about the crystal structures or the structures of the sample. It is simple cubic, body center cubic, or face center cubic. What is this thing? What are the lattice parameters? All the ideas we can get. So this is some, we already discussed about the X-ray diffraction patterns and Bragg's law. Now come to that. So we already discussed about intensity. If we plot the intensity with the function of 2 theta, theta is a glancing angle. In some places diffraction patterns is formed where the intensity is maximum. So these, in this place there are several peaks are observed, okay. Now there are two things on these peaks. If the peaks are shifted, okay, then it show the homogeneous strain. If the peaks are broadened, that will gives you heterogeneous strain, okay. Now what is homogeneous strain? Now the question is, what is homogeneous strain, what is heterogeneous strain? So we already discussed we get the intensity of light as a function of glancing angle theta, from where the diffraction patterns is formed. The maximum peaks will come in those place. So from there we can get some idea about the homogeneous strain and heterogeneous strain. What is those things? What is the why it is important? Okay, and why it is actually, it gives the idea about the defect of the material. So what is homogeneous strain? Homogeneous and heterogeneous strain is, suppose the strain which create the same distortion in the material, then it is called homogeneous strain. Okay, let's see, understand from the diagram, or say this is a material. Okay, it is a rectangular shape of the material. Now suppose we apply some force. Okay, when we apply some the force, it gives some distortion, but in uniform distortion, it will give some uniform distortion. Okay, so this means that it will be slightly tilted, maybe its angle will be slightly tilted, but shape is not changed. Okay, so distortions happen uniformly, so it is called homogeneous strain. Okay, that is also defect, but it is homogeneous. Okay, or if you give some force vertically, it will reduce the size but shape is same, then it is homogeneous strain. In case of heterogeneous strain is the strain which create different distortion everywhere in the material. Suppose this is the initial shape, now we apply some force, for that distortion happens, but that is non-uniform. Okay, or if you apply some force, okay, the shape is, it is distorted but non-uniformly. Okay, so that is called heterogeneous strain. Okay, so this gives some idea about the defect of the material. If any defect is there, that is also, it can be detected from the XRD, X-ray diffraction method also, it's possible. Now come to the Sherry's formula. So what is Sherry's formula? To determine the size of the crystallite in the material. Okay, so that is, the formula is given, D equals to K lambda divided by B beta cos theta. Okay, this is a Sherry's formula. Why it is important? Suppose there is a crystal structure. In the crystal structure, now we know that the there is a regular and periodic array of lattice points. Okay, lattice point which contain the atoms. Now at some points, at some place, that continuity will be break. Okay, at some place it is some, there is a, this structure is regular, continuous, and this one is also continuous, but some place there is a defect occur. In this place, suppose defect occur, that is called grain boundary. So okay, now this is called crystallite. Okay, we can determine the size of this crystallite in the nanomaterial. Okay, suppose how much space is continuous, how much is regular. Okay, that is that size we can determine, that is called crystallite. In the nanomaterials, we can determine the size of this crystallite. Okay, and there is a grain boundary, basically it's a defect in the crystal structure. We can also identify if any defect is there in the crystal structure by using this thing. Okay, now D is the size of the crystallite. How can you determine? We have to give some this K is the Sherry's constant, that is nearly order of 0.9. Lambda is the wavelength of the incident X-ray. Beta is the full width at half maxima. Okay, beta is the full width half maxima of the diffraction peak is there. In the diffraction peak position is occur in the, when you plot the intensity versus theta, where is the peak position is there. From there we can get the theta value, and in this intensity peak, from there we can easily obtain the beta value, full width half maxima of that peak. Okay, so from there we can determine this beta, theta, and lambda value, theta value, K is constant. If we know all those things, we can easily determine the size of the crystallite. Okay, so size of the crystallite in nano size materials is predicted by the Sherry's formula. Any kind of small type of nano materials is there, where suppose any defect is there, or what is the crystallite size is there. To determine those things or to measure those things, Sherry's formula is very important for these things. Okay, now come to the next topic is scanning electron microscope. Okay, what is scanning electron microscope? Okay, so scanning electron microscopes, before going to this discussion, we know about what is microscope. Microscope is basically very small sample will be magnified, right? We know about this. It will be magnified the sample which is very small in size. Okay, there is a main purpose of using microscope, which is magnifying that, and it gives some clear image of that small sample. So that is the called microscope, right? Now the name is scanning electron microscope. I will come each and every word. What is the, why it is called scanning, why it is electron, and microscope is basically magnifying the image. So first, this scanning electron microscopes was first discovered in 1942, and it's commercially produced or used from 1965. Okay, scanning electron microscope provide a very good resolution, high resolution. It is a high resolution microscope. Okay, of very variety of samples, typically is the order of 5 to 10 nanometers. It is nanometers order particle size, which is magnified 10 to 1 lakh times of this sample. Okay, so it gives some very high resolutive or high resolution image of that sample. Okay, but the thing is, it doesn't mean that magnification and resolutions are same. It is totally two different things. Resolution means it gives some quality of that video or image. It gives some more clarity of the image. Magnification is different things. If you magnify it, suppose we take a photo and we magnified that image, okay, in some cases it's little bit bare, like something is coming, it's not clearly visible. So if high resolution means it's highly, that will be not blur, it's not break that quality of that image. So that is called high resolution. So this means we can say increasing magnification does not increase the resolution. It doesn't mean that if you increase the magnification it will increase the resolution. No, it's not that. Resolution is quality of that image. These are different things. Now these are basics structure of the very simple structures of the scanning electron microscope. Okay, I'll first come to the apparatus. After that, I will go for the construction and working principle. Okay, so what is this construction, or what is the simple structure? So this is first is a cylindrical tube. Okay, cylindrical tubes of either it is semiconductors or metallic cylinders. Okay, actually in these cylinders the space is totally vacuum. We create totally vacuum space. Okay, vacuum column, that's why it is called vacuum column. The cylinder is totally vacuum. Now inside this cylinder there are two lenses are there. Okay, one is condensing lens, another is objective lens. Along with that, their scan coils is also used. I will come to the what is the importance of these things, what is the purpose of using these things. I will come to this before, but what is the construction is there. So there is a cylindrical column is there, which is totally vacuum. You create the vacuum space inside these things, and there is one scanning coil is there, which is hold the condensing lens and objective lens. Okay, and there is another electron beam source is also there on the top. From there electrons are comes and pass through these lenses, and after that it comes out and falls on the sample. Okay, falls on the samples. From there the electrons comes out, and that numbers of electrons is detected by these detectors, which is amplified that electrons. Okay, and give some image of those on the monitor. Okay, of this sample. Okay, magnified image of this sample. These are some one line explanation. So scanning electron microscope use electron beams to produce the image of the sample. Okay, so this means electron beams passes through this condensing lens, and it comes out and falls on the sample. Okay, from there electrons beams are comes out from the samples, and those electrons are detected by the detectors, amplified, and from there the monitor is connected with these detectors that will take care about the construction of image. Okay, this is one line description. Now this is the what are the construction is there. This is a very simple structure of the scanning electron microscope. Now, why we use these things? What is the importance of these things? That we will discuss in the next slide. Vacuum column. Why you create the vacuum column? First of all, vacuum column means, suppose this is a electron beam source. This is a electron source, from there electrons is coming, okay. And now if these electrons is coming, now what will happen? Suppose in this tube, suppose there are some particles are there, then there is a possibility those electrons will be interact with those particles and the path of these electron beams will be deviate, okay. If suppose it is deviate, the image will be not formed properly. So avoid to these things, we keep the space is totally empty, vacuum. There is no particles or no airs is be present inside this tube, okay. So that's why electron beams is fall on sample in vacuum, because it is not deviated from its path by the other atoms. If other atoms is there, then there is a chance the electron beams is coming, those are interact, the path will be deviate, so it's not properly falls on the sample, then image will be not create properly. So that's why we create some vacuum space inside this tube. Now, condensing lens and objective lens. What is this lenses? This lenses is the purpose of using this lens. The electron beams is coming and those are falls on this condensing lens. Condensing lens, what it will do? It will basically focus. It will focus the electron beams, okay. It will basically focus the electron beams and it pass through the objective lens, okay. And objective lens, what is the objective lens? Objective lens is also focusing these electron beams and on the object, okay. So this is basically the purpose of using condensing lens and objective lens is focusing the incident electron beams or primary electron beams is coming, that will be focused by these two lens. Objective condensing lens, basically it's condense, the condensing basically condense the electron beams, okay, and it's travel towards the objective lens. Objective lens is it's also focused and focusing on the object, that's why it is called objective lens. After this, the electron beams is comes and falls on the sample, okay. Now what will happen? After these things, it will comes out and it will be detected by the detectors. From there we can got the image of the sample. Now scan coil. What is scan coil? It is very important. Scan coil is this is scan. Scan coil is rotate the coil. If we rotate the coils, it is rotate the lens basically. Scan coils purpose of it's rotate the lens. Suppose there is a condensed lens and objective lens is there. The scan coil is just a holder. It's hold the lenses, okay, and it's holds the lenses means it's rotate the lenses. Suppose it's this one in this direction, in this side it's still in every directions, okay. This means electrons beams will fall in each and every points of the each and every point on the sample, okay. So that is the purpose of scan coil. A scan coil rotate the lens, then the electron beams will be fall on each and every point of the sample, okay. So that is the purpose of scan coil. Why actually a scan coil is needed, little more clarity. Suppose this is a sample size, okay, this is a sample size, electron beams is coming, okay, and fall on this place, okay. So it falls on this place, then from there electrons is comes out, okay, its electrons will comes out. Now we want to take this portion is scanned. Now this portion, another points will also need to scan. So we need to change the directions of the electron beams. How to change the directions? If we change the if we rotate the scan coil, okay, so electron beams will be, if we want to come to these positions, okay, then we need to change the scan coil. It will rotate the lens, corresponding electron beams will be deviate and it will come to this point. In this way it will scan all the points, okay. So it is not a singly take the image of the sample, it takes some times, okay. If every place if you rotate the scan coil, and that's why electron beams will change its position and scan all the positions, all the place of the sample. In this way, the image will be formed slowly, okay, at a not a single times, okay. Diffraction patterns will form slowly, it will scan slowly of the sample, okay. Now what is the, before going to these things, I already discussed what is the purpose of all this segment of this scanning electron microscope. Now come to the principle of the scanning electron microscope. What is the principle of this scanning electron microscope? Suppose this is a sample, okay, samples is there, okay. So now there is samples, there is lot of atoms are there, okay, lot of atoms are there. Now these atoms are there, suppose electrons is comes and falls, okay. So from electron beam source is there, from electron beam source electrons is coming, this is primary electrons, and suppose one of the atom is there, the atoms, this is one of the atom, okay. So we know that what is atomic structures, at the center nucleus is there and electrons are evolving in the orbits, okay. Now this is this electron beam, this is a primary electrons which is comes from the electron beam, from here it is coming from these electrons is coming from electron beam source, okay, these are primary electrons. Now there is, suppose one of the atom is there, okay, this is the one of the atom is there, okay, these atoms we target. Now what will happen, these atoms, nucleus is there, another electrons is evolving on the different orbits. Now these primary electrons comes and falls on these atoms, okay, and after absorbing these electrons comes out, okay. So these are primary electrons is coming, passing through this lens, falls on the sample, and after that these electrons is a secondary electrons. After absorbing these things, these electrons comes out from the atoms, this is called secondary electrons. These secondary electrons detected by the detector, okay. So in this way, electrons will be, number of electrons will be detected by the detectors, okay. Suppose in some places atoms is more, okay, so when the more electrons beams is fall, the more numbers of electrons will comes out, that will give some white color. If suppose few numbers of atoms is there on the sample, in some place it is, suppose the atoms are not uniform, some places very high numbers of atoms is there, in some place few numbers of, moderate numbers of atoms is there, okay, in those cases, when in these cases when the electrons beams falls on these things, electrons comes out, but that is less numbers of electrons, that will create gray color. In some places there is no atoms, okay, there is no atoms is there, so when the electrons comes out, no electrons will comes, so it will give some black color, okay. So in this way the detectors will count the numbers of secondary electrons. If more numbers of secondary electrons will be detected, that will give some white colors of the image, okay. It will give some, yeah, there is high numbers of electrons is there, high numbers of atoms is present there, so it's that place. Some region less numbers of atoms is there, that will give some gray color of that image, okay. In some place totally nothing of the atoms is there, that will give some black color of the image. So in this way you continuously rotate that scan coil, and from this, and the electron beams is coming, due to the rotation of the scan coil, it will rotate the lens. If lens is rotated, the electron beams is passing through these things and it will fall in each and every point of the sample, okay. In this way it will scan the sample, okay, slowly it will scan, not a single time it will scan, it will scan each and every point of that sample, and when these electrons goes to these primary electrons go or fall on the sample, then what will happen, atoms will absorb that electron beams, and after that what are the electrons evolving in the orbit of that atoms, one of the electrons maybe comes out from the valence orbit which is loosely bound, that is called secondary electron. That secondary electrons detect by the detectors, okay. If it detect, and it will amplify those electron counts and create some image of that sample. White colors in the image, it gives them that there is a huge numbers of atoms is present in that region, and gray color means it is a moderate numbers of atoms is there, in black colors means there is no atoms is there. In this way slowly you scan the sample, over the sample, and slowly the image will be formed. Okay, total it takes some time in this way, like a scan. How we scan these things at a time, so we scan, you some scan in this way, like there is a we know in our printer, suppose we keep some page. Okay, what will happen is, suppose we keep our page, and what will happen, the light will comes, there is a one light color light is comes and pass through this thing, right? So it will first, each and every positions of this page will be scanned first. Okay, so in this way, similarly in scanning electron microscope, sample is not a scanned at a single time. So it is not a very quickly sample, continuously it takes each and every points of that, it will scan the each and every point of the sample. Okay, and slowly it create the image of that sample. Okay, so that's why its name is scanning electron microscope. Scanning means it scan the sample, electron means you use the primary electrons, and the electrons comes out from the sample, those are secondary electrons. So that's why it is a scanning electrons. Electron beams are using, and detectors also collect the electrons from the sample, from there you can get the image. That's why the name is called scanning electron. And microscope is from the number of count of those electrons, it produce the image of that sample, which is magnified image. That's why the total name is scanning electron microscope. Okay, so today it is the overall discussion about this X-ray diffraction methods, Bragg's law, and overall different type of power, different type of methods we use to determine the crystal structure. So this is the overall idea about this, how to determine the crystal structure. So today I will finish it here. Thank you.